Good morning, good afternoon, good evening, everyone. For those who don't know me, my name is Kelly Lyons, and I'm a professor in the Faculty of Information at the University of Toronto. And I'm currently serving as Acting Vice Dean of Research and Program Innovation at the University of Toronto School of Graduate Studies. I am also a faculty affiliate at the Schwartz Reisman Institute for Technology and Society. Welcome to the sixth and final session of the Women in AI speaker series. It's been great to have so many attendees join us for such a wide range of engaging, enlightening, and empowering presentations from so many female researchers working at the forefront of artificial intelligence and data-driven technologies. And today is no exception. A collaboration between the Schwartz Reisman Institute and Deloitte, the purpose of this series is to convene leading female researchers to share knowledge and mentorship opportunities for women across the technology sector with a particular focus on artificial intelligence. Participants will explore the development of new technologies and approaches and insights into cutting-edge research from the perspectives of our esteemed guest speakers. To begin today, we want to take a moment to acknowledge the land on which the University of Toronto operates. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. These and other Indigenous peoples across Turtle Island developed complex and effective governance systems based on respect for all life and the intelligence of the natural world. Today, this land is still home to many Indigenous people working to reclaim their rights to self-governance, and we are grateful to have the opportunity to live and work on this land. Although we may all be joining from different places, we encourage you to reflect on the history and relations of the land you are on. Before we begin today's talk, I'd like to introduce our collaborator in the series, Aisha Green. Aisha is a senior manager at Deloitte's AI Institute, focused on AI literacy and adoption. She is passionate about fostering partnerships which advance research and innovation initiatives and has worked closely with early-stage entrepreneurs to commercialize medical devices, therapeutics, and information technology applications. Welcome, Aisha.
Thank you, Kelly, for that warm introduction, and good morning or good afternoon to everybody around the screen. It's such a pleasure to have this series that we have established together, and it's so grateful that we heard such wonderful stories and experiences and research across the research spectrum. Now, robotic systems coexisting and interacting with humans, no longer that premise of science fiction. As research expands into how we use robotics to perform specific program tasks, it's clear that the opportunities that lay before us are endless. It's important, however, to understand that robotics and artificial intelligence are two different things. While AI seeks to emulate the human mind and learn and solve problems, robotics are programmed to perform very specific tasks and duties that are predictable, repetitive, and sometimes very difficult for humans. Despite this, we are seeing increasingly an overlap between robotics and AI, and even more sophisticated ways. From our esteemed researcher today, we will hear how robotic systems are being designed to coexist and interact with humans. We'll also hear what it means to be a woman within this space and how our speaker has navigated her career path to ensure that her work has a broader impact on the world in which we live. Our hope is that the conversations that you hear and the networks that you begin to foster through this series will fuel change that is vital for this sector for both women and allies. With that, I hand it over to you, Kelly, to introduce our esteemed lecturer for today.
Thank you, Aisha. A few quick notes before we begin. The session is being recorded. Our guests will speak for about 45 to 60 minutes and will take questions after the talk. During the Q&A, we encourage participants to use the raised hand function in the Zoom meeting controls to ask a question, and I'll call upon you. To facilitate the discussion, we also invite you to please update your display name with your first and last name. So now it's my pleasure to introduce Maren Bennewitz, who is a professor for humanoid robots and Vice Rector for Digitalization at the University of Bonn, an executive board member of the Cluster of Excellence FENOROB. Her research focuses on robots acting in human environments, and in the last few years, she has been developing several innovative solutions for robotic systems coexisting and interacting with humans. Among them are machine learning techniques for efficient navigation with humanoid and wheeled robots, as well as for reliably detecting and tracking humans. Maren has published over 100 peer-reviewed scientific papers and regularly serves as editor or associate editor for top-tier robotics conferences and journals, and as a program committee member for international workshops. She also serves as a reviewer for the European Commission and the German Research Foundation, and has been a principal investigator in several national and European projects. Without further ado, Maren, the floor is yours.
Thank you for the kind introduction. I'm really excited to be here and give the presentation. I try to share my screen now. Let's see. So do you see my presentation, clear mode?
Yes, we do.
Perfect. Let me arrange some Zoom windows. Okay, should work now. Yeah. Thanks a lot for the invitation, as I said, and since this is a broader audience here, I would like to first introduce you to some basics in robotics. So consider the scene. The robot is standing in front of a plant, and this is a current camera view of the robot, obtained with the camera on top of the robot here. And using standard image segmentation techniques, the robot can obtain estimates about the classes of objects in its field of view, like, for example, is shown here on the next slide. So you see here, the robot knows semantic information about the environment. This is a chair here, this is a table, this is a plant, this is like a sweet pepper, these are leaves. The robot can obtain this information by analyzing its RGBD image obtained with its camera. And when combining this semantic information with the depth data from the depth channel of the same camera, the robot can get information about the relative position, so distance to the camera, and the size of visible objects. This is illustrated on the next slide. So here you see a visualization of the depth data obtained with the robot's camera. You see, for example, that objects close to the robot's camera, like these leaves here, are visualized in red, and objects far away are visualized in like yellow, or more distant objects in green or blue, like here the pot, for example. And depth cameras have only a certain range in which they can measure objects, like 25 to 70 centimeters, for example. So objects that are far away from the robot's camera cannot be seen. So to summarize what we have just learned, from the data of the RGBD camera on the robot, it can estimate semantic labels corresponding to object classes in the RGBD image, as shown on the left here. And additionally, the robot obtains distance information about objects from the depth information of the camera. So using a combination of color and depth data, the robot has an estimate about the type, relative position, and size of detected objects. So coming back to the original topics of this presentation, what can such labeled data be used for? So it can be used for foresighted robot motion planning, utilizing information about obstacle classes. So the robot can reason about how to overcome objects that are in its way. And it can perceive users and predict their motions using information about objects the users interact with. And using this prediction, the robot can then choose, for example, trajectories that do not interfere with humans moving around it. So how do robots actually solve navigation tasks in general? Consider this simple example. This is a bird's eye view of the environment of a robot, let's say. And the task of the robot is to move from this location here to this goal location. And how can the robot plan its path to the goal location? Well, we first discretize the environment. So the robots typically use a cost grid for motion planning. So as a first step, we approximate the environment as such a 2D grid. And then we obtain a cost grid that is used for motion planning by first marking each grid cell that is occupied by a static obstacle as non-traversable. So all those black cells here correspond to cells that are assumed to be occupied by a static obstacle. And then the navigation cost of the remaining cells first depends on the distance to these obstacles, as shown here. So cells closer to static obstacles have a higher cost since there's a danger of collision. And the cost of the remaining cells depend on the time to execute actions. For example, turning and moving forward have certain costs. And when we have such a cost grid, the robot can then plan its path in this cost grid using standard path planning techniques. So for example, this here would be the path with the cheapest overall costs. And the path costs are just the sum of the cells on the path. So these were the basics that are needed to understand the topics of my presentations, which I'll start now. So why do we need foresighted navigation? Well, service robots acting in human environments should avoid interferences with the users and act foresightedly. So they should not, they should adapt their behavior to the users and not vice versa. And in the following examples, you see 3 examples for undesired robot behavior. For example, here, the robot and the user are somehow stuck. So the robot is blocking the way of the user, which is not desired. In the second example, the robot closely follows the user, which might be annoying. And in the third example, the robot is too far away from the user, so no fast reaction would be possible in case the user needed help. So these examples should illustrate that the robot should be able to anticipate human movements and then adapt its own navigation behavior accordingly. Furthermore, robots should not just treat objects or obstacles as static, but distinguish between different types of obstacles and reason about how to overcome those obstacles. For example, here, there are several objects in the way of the robot. Like blocks like those here could be stepped over by the robots, balls could be kicked away, and stuffed toys like those ones here could be moved out of the way of the robot. So problems to be solved by service robots acting in human environments are first, as I said, motion planning and navigation through cluttered regions. And second, the prediction of human motions for foresighted robot placement and navigation. So the robot should anticipate when and where assistance is needed, as well as avoid interferences with the user. And in the following, I will present 2 approaches that we developed for those problems. So first, a robot that navigates through cluttered scenarios has to reason about possible actions about how to overcome the objects. And for that, complex actions are required. So the robot needs to calculate whole body motions and also manipulate objects in order to move them out of its way. And the challenge here is that finding a detailed plan of all possible motions and object manipulation actions to reach goal locations collision-free is time-consuming and computationally expensive, since many different solutions exist, and also the robot has a lot of degrees of freedom, a lot of joints. And so our idea is to exploit knowledge about different obstacle classes to choose appropriate robot actions. So in this example, the robot has to navigate through an area where objects are impeding its way to the goal. So the goal of the robot is somewhere down here in the hallway. And you see there are several objects in its way. And the robot can now either move aside, for example, this stuffed toy here, or perform like footstep planning over those toy blocks here. And in this case, the robot chooses to pick up and move aside the stuffed toy in order to reach its goal location. And I will explain now our approach, how we come up with such a navigation plan. So we first, an overview of the individual steps. So we first use a convolutional neural network for pixel-wise segmentation of the RGBD image and obtaining class information about the obstacles which are in the way of the robot. Then we estimate for each object class the cost of possible actions that can be carried out to overcome the obstacles. And these action costs depend on the execution time of the actions. And then we encode those action costs in a 2D cost grid of the environment and use this map for fast path planning. And the path then inherently contains the necessary actions that the robot needs to execute in order to reach its goal location. The individual steps are now illustrated on the following slides. So as I said, we first train a convolutional neural network for pixel-wise object segmentation. So you see here as input, the robot, the input to the convolutional neural network is the current camera image of the robot. Then some convolutional operations are performed, and as output, the robot gets a segmented camera image. So in this case, it knows that the green pixels here belong to a book that lies in its way. So then we need to define actions to overcome the obstacles. And these actions need to be chosen for the robot type, for the robot that is applied in the application. In our case, it was a small now robot, which you have seen on the previous slides. And the application was that the robot had to navigate through like children's rooms with many toys on the ground that the robot had to overcome or move aside in order to reach goal locations. So we use the following object classes and the associated actions, which are contained in this table here. So for example, for balls, the robot can push them away, step over them, or pick them up, depending on their size. Then we have cars and toy blocks, which can be stepped over or picked up. We have stuffed toys or dolls, which can be picked up, and we also have boxes and books, which can be stepped onto or picked up. Of course, different robots can perform different actions, and also depending on the application, we can have different object classes, but these action types can be easily defined and adjusted accordingly. So as I said, for path planning, we use action costs corresponding to the obstacle classes. So first, we use depth data to exclude actions depending on the size of objects. So as you have been introduced in the beginning, from the depth data of the robot, we can estimate the size, the volume of objects. And based on the estimated size of objects, we can exclude them when they are too large for the robot, for example, to carry them away. And obstacles which with an unknown class or no executable action are considered as static, which means they can not be moved by the robot and are thus have a very high cost, which is contained in the grid map. And what we do then is we assign the cheapest possible action to each detected object, and then include these actions in the cost grid and perform path planning. So how can we actually calculate the action cost? So we calculate the action cost based on the time needed by the robot in order to carry out the corresponding action. So we define the cost of the actions according to the estimated completion time, which means that we measure the time it took the robot to reach a goal in a certain distance, by just walking to the target location, or by additionally pushing a ball out of his way, or by stepping onto a box, or by carrying aside an object. So based on these estimated execution time, we assign action costs to the individual actions. How do we use the obstacle information for path planning? So as I said, the robot detects the object in its current camera image and then projects the detected obstacles with their corresponding action cost onto a cost grid of the environment, and then searches for the cheapest path to the robot's goal location in this cost grid. And the obtained 2D path contains the necessary actions in order to reach the goal location. I will show a complete example now on the following slides for this process. So here you see the robot's current camera view. And as said, first, this camera image is segmented with a convolutional neural network. So the robot knows that those pixels here correspond to toy blocks and those here to a doll. So we get a pixel-wise segmentation of the current camera image. For each pixel, the robot knows to which object class it belongs. Then using the depth information, the robot can estimate the distance to these obstacles and projects them down onto a map of the environment, as shown here. So maybe a few more words here. This is a top view of the environment. The robot is standing here. This was a current image, camera view of the robot. The black cells correspond to the static parts of the environment. So the robot has a map of the environment containing the static obstacles which are not movable by itself. And then these cells here correspond to the projected obstacles detected in the camera view of the robot. So given such a segmented camera image and the corresponding depth information, the robot projects this information down onto a grid map of the environment and can then perform path planning in this map here. Just to explain again, for example, here you see a wall on the right side of the environment, and this would correspond then to that wall. So this is really a top view of the environment, which is used by the robot for path planning. So we transform then the obstacle information on the left into action costs, which means here that we have high costs for this area where the doll is located, and also here higher costs where the toy blocks are located. And given such a cost grid, so darker color means higher costs, the robot then performs path planning from its current post to the goal location. And as you see here, the cheapest path leads over the toy blocks. So the robot would move here, perform footstep planning over those toy blocks to reach its goal location. So given such a calculated path, the robot can then execute this path, perform footstep planning over the toy blocks, and reach its goal location. To execute the plan, it is split in different parts. So path segments where no objects are, the robot can just perform standard walking along the 2D path. So it does not need to consider actions in order to overcome objects. And for path segments which contain actions, the robot performs local reactive action execution that contains also the planning and execution of whole body motion. So for example, for push or pickup actions, the robot walks to the last free grid cell on the 2D path and then executes the corresponding actions using the currently obtained segmented point cloud. And for stepping over or onto actions, the robot performs 3D footstep planning in the corresponding region of the height map, which is computed from the point cloud. I have a video illustrating this process on the next slide here. So first I explain what's going on. So the robot has to walk from this location here to some target location down here. This is an overview of the scene. Here you see the grid map representation of the environment. The black cells corresponds to the walls and the static obstacles contained in the environment. The green path is the currently best, so cheapest path calculated. And when the robot starts moving, it will detect that objects are in its way. I start the video now. And when the robot starts moving, wait a sec, why is it not starting? No. Yeah, so the robot starts moving. The objects get in the camera view of the robot soon, as you will see. So the robot detects some toy blocks here and the stuffed toy. And initially the shortest path leads over the toy blocks. But as the robot continues moving, it realizes that there are several toy blocks actually. So it's cheaper to move away the stuffed toy. So the robot moves close to the stuffed toy, picks it up, and puts it out of its way. So now the path is freed. The robot updates its environment representation. As you will see here, the path is now free, and the robot continues walking towards its goal location. And I have a second example here with the ball and the box. And in this example, the robot decides to kick away the ball to free its path. The environment representation is updated, and the robot is able to reach its goal location. The ball actually bounced back from the wall, which cannot be seen in this image, but this is why it is included here in the cost grid of the environment. So another example in simulation is here. In this case, the robot has to move to a location behind the wall here, and there are several blocks impeding its way. And initially, the current footstep plan leads through the toy blocks. But as the robot comes closer to the toy blocks, it actually notices that footstep planning cannot find a solution crossing the toy blocks due to the configuration of the blocks. And the action is changed accordingly. So the robot decides to first move aside one of the blocks to free its path, or let's say to be able to perform footstep planning across the blocks. Okay, so this example showed you how image segmentation techniques combined with action costs and path planning can be used in order to calculate appropriate actions of the robot in order to overcome objects in cluttered environment and successfully reach goal locations. Now I want to move to the second part of my presentation. So the prediction of human movements is important for a service robot to anticipate when and where service is needed, as well as to avoid interferences. So I will present you an approach that we developed for human motion prediction in order to realize such foresighted robot navigation behavior. So one observation is that humans typically move between objects with which they interact before moving to the next objects. So in this example, the robot interacts with a cup, and the most likely next navigation goal is a table. And the robot would then move close to the user in case help or support would be needed, but at the same time avoid interferences. And our approach to realize such foresighted behavior is to learn transition probabilities between user-object interactions. So basically, these transition probabilities tell us if a user interacts with a certain object A, how likely it is that it will interact with object B at the next time step. We use a map of the environment with a location of relevant objects in the environment of the user, and we then integrate observations about the user and detected object interactions to predict the user's next navigation goal. And in this way, the robot is able to react quickly if service is needed. So it can use the prediction in order to place itself close to the user, but at the same time avoid interferences with the user. So it realizes foresighted navigation behavior by choosing poses that are close to the user, but not too close so that the robot is not in the way of the user. I will explain in the next slides details about the individual steps. So first, to learn transitions of user-object interactions, we developed an approach to extract general user-object interactions from RGBD videos. For that, we first trained a convolutional neural network for object detection, as we did also for the previous approach. And we then deployed a system for the detection of the user and the estimation of their body pose and their orientation. And we detect user-object interactions based on objects the user is oriented to, and based also on the information whether they are touched by the user. So we estimate the user's orientation and the hand position from the estimated body pose, and then check whether there is an overlap between the object bounding box and the hand position. And we check whether they are also close in depth. So consider this example here. The user is orientated towards the coffee machine, and there's an overlap between the coffee machine and the hand position, and they are close in depth. So our system then detects that there's an interaction of the user with the coffee machine. Here I have a video illustrating how that works in practice. So on the left, you will see detected human object interactions. And on the right, you see the detected user, the detected pose, and also the detected objects. So initially, an interaction with the laptop is detected. Afterwards, a user starts moving, grabs a coffee cup, which is also detected. And finally, the robot, the user interacts with the coffee machine. Okay, so we use such data to extract human object interactions from training data. And then we derive transition probabilities between such object interactions. So these probabilities tell us, as I said, if the user interacted with an object A at the previous time step, how likely or what is the distribution about the next objects the user will interact with. And we use also knowledge about the locations of objects in the environment to infer then likely navigation goals of the user and predict human motions, because this is our ultimate goal, that we predict where the user will move to. In this example, the user is interacting with the cup, and based on the learned transition probabilities, the likely navigation goals of the user will be a coffee machine. So a coffee machine appears twice in the environment, like here and here. Or it could also be that the user moves to a table indicated here and here, or a chair like those ones here, or even a refrigerator as indicated here. And the idea is now to use observations of the user's movement and orientation in order to infer the next navigation goal based on this detected interaction with the cup. So as I said, objects of certain classes can appear several times, like with the coffee machine, the table, or the chairs. So we integrate also observations about the user's movement and their orientation to get a probability distribution of the next navigation goal of the user. And for that, we use the inverse distance of the user to the objects and also the inverse orientation difference of the user towards the objects. So basically, the closer the distance between the user and an object, the higher the likelihood that the user approaches these objects in the next time step, and the same for the orientation. So in this way, we get a probability distribution about the user's next navigation goal. And now the question is, how do we use this probability distribution, so this belief about the user's next navigation goal, in order to determine the best position for the robot to be close to the user in case assistance is needed, but also to be not in the way of the user. So we evaluate possible positions for the robot using a cost function. And here we take into account the distance to the user's possible navigation goals, weighted by their calculated probabilities. So you see here, objects in darker green are more likely to be the next navigation goal of the user, and cells with itself there. So for example, this here is the best robot position for this example, because it's basically closest to all possible, all likely navigation goals of the user. So from this position here, the robot can reach quite fast all possible likely navigation goals of the user. So using this, the robot can calculate the best position for itself, but the question is, how should the robot move to this position? And for such path planning, we consider constraints that are derived from from studies about human comfort. So there are 3 zones around the user that should be considered by the robot. First is a social zone, which is a circular area, like an interpersonal space around the user, that the robot should not enter because users get annoyed by the robot then. And we also have the information process space in front of the robot, that the robot should, in front of the user, that the robot should also not enter because the user considers objects which are in front of it as obstacles and does not like the robot to be in front of it. And we have then an area behind the human which has increased cost. So the closer the positions to the human, the higher the cost, but the robot can enter those regions here. So as I said, we have calculated before the best robot position using the distribution about the user's next navigation goal. What we do then is we predict we first calculate the most likely navigation goal of the user, which is this one here, and then we predict the user's path to this most likely navigation goal, which might be this one here, for example. And then we apply time-dependent path planning for the robot to its best position, considering the human comfort constraints just introduced. And whenever the belief about the user's next navigation goal changes, everything is updated. So then the best robot position is recalculated, the predicted user path is recalculated, and also the best robot path is updated. And this is shown in the next video. So you see here an overview about the, again, a top view of the environment. So here is the user indicated and also its orientation. Here we have the current robot position and orientation. So it's basically facing the user. This is the front RGB, the front camera of the robot. And the robot then detects object interactions as before, predict the user's navigation goal, and will calculate the best position and path for itself. I start the video.
Based on observations and prior knowledge about object transitions, the robot predicts the movement of the user. Objects are colored in green if they are likely navigation goals. The darker the green, the higher the likelihood. Using the prediction, we compute a time-dependent cost map and an optimal position of the robot on it. During an observation update, the robot notices that the user did not follow its prediction and recomputes the cost map based on the new prediction. As the robot observes the user entering the room, it again corrects its prediction and updates the cost map accordingly. As the user leaves the room, the robot needs to adjust its movement to avoid entering the social zone of the user and updates the prediction. Once the user stands still, the robot uses its chance to pass by and reach the goal before them. The final prediction was correct, and the robot arrived on time at the navigation goal of the user to provide assistance.
Okay, I'm sorry, I couldn't stop the sound somehow. Zoom didn't, or PowerPoint didn't let me. So this example showed you how the robot continuously adapted the belief about the user's next navigation goal and recalculated the best position for itself. And finally, the robot arrived earlier than the users at the final navigation goal, and thus the robot would be able to provide assistance to the user directly if needed without being called, let's say. This was what I wanted to show and explain in the video, but I apologize for the sound problem. So we extended this work recently, so we predict now not only the next navigation goal, but a sequence of navigation goals of the user and infer where assistance is actually needed, and then the robot chooses its best position accordingly. We include also context information, so in which room the user is, which activity is currently executing to choose the best robot path. So for example, if the robot is currently working on a laptop or during a phone call, the user might not be wanted to be disturbed, so the robot should choose like a larger detour in order to carry out its tasks. And we also include general user-desired factors such as unobtrusiveness and predictability in the calculation of the robot path and trajectory. And then we have a very recent ongoing work. So we want to learn personalized robot navigation behavior. So like the path of the robot and also the velocities with which the robot drives. So basically consider your personal service robot at home. You might want to define how close the robot should come to you, how fast or slowly it should drive around you, and should it pass in front or behind you, for example. And it would be great to have a system that lets you teach your robot this navigation preferences. And this is exactly what we developed. So we developed a virtual reality interface in order to demonstrate example trajectories to the robot so that personalized robot navigation can be achieved. So as you see here, the person uses a handheld VR controller, and in our VR interface, the user will see a beam with which it can draw the preferred trajectories onto the floor. And then the robot can learn about the preferred navigation behavior from the user. So which distance it should keep, how close it should be to furniture, for example, and those kind of things, so that you really get a robot that follows your personal navigation preferences. Here you see an example in our virtual reality interface. You can see how the user draws preferred trajectories onto the floor with a handheld controller. And then you also can see how the robot and the user move in the environment. The user can adjust or evaluate the learned trajectory. And also the trigger on the backside of the controller allows the user to select the robot speed along the drawn trajectory. And the robot executes the demonstrated trajectory right away in the virtual reality. And as I said, allows the user to either keep the trajectory or redo it. And using this interface, we get a set of demonstration trajectories for the robot, like preferred robot trajectories, which are then used as input into a reinforcement learning agent. So we have developed here some imitation learning framework to maximize the reward and learn human preferences regarding robot and angular velocities as control commands for the robot. And the robot then executes these actions in simulation, gets the reward, and changes to the next state. And this process is repeated until convergence. So just a few words about the state transitions or the used state space, let's say. So we use a robot-centric state space. The robot is indicated here. We use a distance and relative angle towards the user, and also the relative angle towards the navigation goal. And as a further context variable, we also use body orientation relative to the robot. And additionally, we use the distance and relative and closest obstacle. This is a state space. And as a reward function, we use a sparse reward that contains 3 different terms. And these terms are designed to avoid collisions, of course. So the robot gets a negative reward when a collision occurs, and it gets a positive reward when it reaches the goal, and also a negative reward when it does not reach the goal location after a certain amount of time steps. So we want to avoid inefficient actions by penalizing behavior where the goal is not reached by the agent after a certain number of time steps. So to explain you how the learning or the teaching of the behavior and the learning and then the evaluation was designed in practice. So we invited a certain number of participants, like 24 in this case, and demonstrated them the virtual reality interface with which they can demonstrate the preferred navigation preferences, which I showed before. This was the first session, so we recorded a certain set of trajectories for each user individually. Then the training of the robot controller took place. And later on, we then evaluated, or we invited the users again for the evaluation of the learned controller in the virtual reality interface, and also using the evaluation on the real robot. Here you see 2 example trajectories that were learned using our approach. So on the top row, we have a user that the user is centered is always placed in the center here. These are the trajectories which were the learned trajectories. And as you see, the learned trajectories closely follow the learned trajectories. Sorry, the learned trajectories closely follow the demonstrated trajectories. And what you see here, the difference to user B preferred trajectories which are as far away as possible from itself. And also those trajectories were learned by our controller. So both users individually taught the robot trajectories, how it should drive around it. And as you see, the controller followed the taught behavior. Besides the trajectory shape, the users can also demonstrate speed profiles along the demonstration trajectories using the trigger on the backside of the controller. And as you see here, for example, this user taught the robot to first drive slowly and only accelerate when it drives slowly, and then accelerate it after it passed the user. So the users can teach the robot not only the shape of the trajectory, the distance, but also the velocity profile along the trajectories. Here's an experiment with a real robot based on the learned trajectories. You see here a generalization. So we used random robot start points that were not included in the demonstration data. and still the robot navigation behavior reflects the characteristics of the learned trajectories from the demonstration. So it first moves away from the user and then approaches the goal location. We performed user studies in order to evaluate our VR interface and also the learned navigation behavior. And as you can see here, the users found it very comfortable to interact with the virtual reality interface and draw the trajectories in the interface on the ground using the light emitting controllers. And what's also very important, of course, is that they felt that the taught navigation behavior was actually reflected in the learned control, was evaluated much more positively than the other navigation controllers. The users are really comfortable with the robot's navigation behavior. So, yeah, I'm actually at the end of my presentation already. So I presented you 3 different topics of our research. So in general, we are dealing with foresighted robot navigation in human environments. And I first explained an approach how we can exploit knowledge about different obstacle classes during path planning through cluttered scenes. So the robot here treats objects not just as obstacles, but reasons about how it can overcome the derived from the execution time. And then we can calculate the robot's path in the 2D grid of the environment. And this path implicitly contains all necessary actions to handle the objects, so move them out of the way, for example. So we have a fast path planning approach on the grid map and leave out the details. We do local path planning during action execution later. Second, I presented an approach for predicting human motions and anticipating where service may be needed. For that, we first learned sequences of human-object interactions from RGBD data. So we basically learned transitions between human-object interactions and used them to infer the user's likely navigation goals and predict the corresponding user paths. And in this way, we can realize foresighted robot navigation and plan their personally preferred navigation behavior using a virtual reality interface. Yeah, so these were the 3 approaches to realize foresighted personalized robot navigation behavior. Thanks a lot.
Thank you, Maren. Fascinating talk and such fun videos. I really enjoyed watching the stuffy get picked up. Of course, there are more important things to ask questions about. And so I already see that Aisha has a question in the chat. Aisha, do you want to turn your camera on and ask the question?
Certainly. And thank you, Maren, for such a fantastic and interesting conversation and review of your research. So curious to see how, or if at all, you're considering the use of generative AI to teach and train just some of the navigation and approaches both in human environments for these robots and even potentially other obstacles for even retrieval that might be used for some of these robots as well.
I'm sorry, could you repeat the question? So my Zoom meeting was...
Yeah, it seems like it's a little bit delayed. Yeah, so curious to see if you are using generative AI for training data for the robots, and also if at all you're using it for retrieval for different scenarios.
You are referring to object detection now, or to which kind of?
Object detection.
Yeah, okay. So we are using standard data sets to train convolutional neural networks and start from pre-trained models, but adapt them to our scenarios. Yeah, we don't train from scratch, but use pre-trained models and then use like enlarged object sets in order to adapt them to our application scenarios.
Okay, are you at all exploring generative AI in order to adapt those models as well? I may have, it seems like Maren might have dropped connection.
We'll just wait a minute. People can start.
The Zoom session.
Okay, yeah.
Something is not smoothly working.
All good. I think we have you back right now. I'll defer and maybe go to somebody else's question just to give other folks some chances to ask some questions as well. And I think Maren might have just dropped.
So I turned off my video.
Turned off your video. Okay.
Someone told me in the chat.
There will always be, we need a robot to help us with our Zoom. So we have a couple of questions in the chat. I'll ask Miriam to ask their question, please.
Okay, I want to know if I can work on robots and virtualize the robots without physical robots.
Sure. You can either work in standard simulation environments, which are available, or using some virtual reality interface. But what are your plans? So what exactly do you want to study in robotics, like navigation, human-robot interaction? So do you already know that?
No, I don't have enough information, but I want to pursue my PhD in robotics. I'm so interested in that.
Miriam, it sounds like there are going to be opportunities for you, and as you explore it more.
Okay,
yeah,
I got my answer, and
good.
Thank you.
Thank you. Vanessa, I'll call on you next once we have Maren back.
I'm here, I can hear you, but
perfect. Yeah. Okay, so Vanessa has a question for you.
So my question is really about, you were talking about the human object interaction and then pathways and predicting pathways that the human is likely to then take. And in much the same way you can then apply that to the robots. And I was actually just wondering, do you see that there's an application for something like that in process analytics? So when I say process analytics, I'm thinking about things like trying to predict where mine cars go missing, or where things in process become a little bit tangled and are not following as they should, for instance. I mean, can you see an application for that? I mean, how would you feel about taking that robotic research that you've done and applying it to something that has got nothing to do with robots, essentially?
Again, I'm sorry, I didn't fully understand the question. There are connection problems. I don't know why. Could you just shortly repeat the question, as long as the connection works?
So when you were talking about human and object interactions and being able to map the likelihood of those interactions or those pathways, do you see an application for that in process analytics? And by process analytics, I mean looking at a business process, procure to pay, invoicing to cash, or something like that, and actually applying it there.
So you mean in company environments, like? Exactly.
Yes, I do.
Yeah. I mean, you can actually also use this approach not only when robots are deployed in the same environment, but for general human motion prediction, right? If you have like a camera, it depends on the application. So what do you have in mind? Do you want to have a robot or having the users, let's say?
So I'm thinking, so for example, one of the projects that I worked on, or that my company has worked on, was looking at where mine carts go in a mine and where they're not following proper process, or where there's a risk of a vendor not following proper process in the tendering process. So that's really what I'm thinking about when I say process analytics. It's any business process where things have gone awry, not necessarily using a robot in any sort of sense, but actually mapping out with data or being led by the data to say, where is this process going wrong? And then how do you predict what possible deviations there could be in that process?
Right. Yeah, for that you would need to learn typical transitions between process items, right? And from that you can make predictions about what will happen next.
Okay.
Sounds like a fascinating project that you're working on, Vanessa. Very important one. So maybe we'll move to Ken next. Ken Myrick.
Hi, how are you doing? My question was more concerning how you feel going forward concerning a lack of regulation concerning AI behaviors.
Hopefully the connection worked and Maren heard the question. Just give that a second.
No problem.
Well, that's a good question.
I'm here, but I don't know what's happening. The connection is really unstable. So I'm at the university with the best possible line, but I don't know what's possible. I'm sorry.
No, it's okay.
Go ahead again, Ken.
Sure. I was just asking, how do you feel concerning fears of lack of regulations concerning AI behaviors that are recently being displayed, such as some of the ones shutting down or not giving correct feedback appropriate to questions asked?
So it might be helpful since audiovisual is not working. Maybe we can get Maren to write. Going back to sort of old-fashioned, if maybe typing in your questions in the chat and then responding that way might be a way for us to get a few insights for Maren. And I know, Ken, you had typed your question. If you can type it again, maybe we can get that dialogue going. Important topic to start to just have a conversation around regulations and policy of any fast-moving technology. So just want to make also the distinction between robotics and AI. Robotics really it's predicted sort of outputs that we put into any sort of machine, while AI, it does have its flaws in how we filter in information as well. But obviously both require regulations and information. But do encourage you to type your questions, and we'll see if we can get Maren to see if we can respond that way.
Sure. Thank you.
Yeah. I will try, but I have a question. Did you actually, could you actually follow my presentation, or were there also connection problems?
No, the presentation worked very well, actually. And
okay,
and what I think,
so I don't know why the connect.
Okay, I'm just going to post Ken's question in the chat again, and we'll let Maren respond to that. Oopsie, I don't see it. I can't do a copy paste, but Maren, if you could just
broke afterwards, really strange. Okay, I'm sorry.
Okay. Ken's question is, how do you feel concerning fears of lack of regulation concerning AI behaviors? And if you just want to maybe type something in the chat, and then I think we'll maybe wrap things up, sadly. But if you have an opportunity to do that, it would be really good.
So I'm in the chat, I can answer questions, and I apologize, I don't know what's going on here, but I'm happy that you could follow my presentation without any interruptions.
I apologize for the issues with the connection. It has been a very smooth 5 talks in the series, so we were, kind of due for a bit of a hiccup, but I am pleased and thankful that we could hear Maren's excellent presentation very clearly. And I do know that we have another opportunity with the Deloitte team coming up, and we'll have an opportunity then to share wisdom with the team. So I just want to say thank you to everyone again. Thank you for your patience. Thank you to Maren for an extremely engaging presentation. And please visit the SRI website, Twitter, LinkedIn to learn more about upcoming events and programming, and the rest. We'll see you at another time. Thank you so much.